Okay, the one more example that I have in mind has to do with certain homomorphism that I can construct from the group of n by n invertible matrices with coefficients, with entries in R. So, what's that homomorphism? So, note that determinant gives you a map from GLNR to what? Okay, so what can you get as a determinant of an n by n matrix with coefficients in R with non-zero determinant? Well, you can get a non-zero real number. So this gives you a map into R cross, okay? And I'm going to treat this as a group under multiplication. So maybe let's just write this down. So if we treat R cross as a group under multiplication, then this is then determinant is a homomorphism. Why is that? So we would have to check that if I take two matrices, so if A and B are two matrices inside GLN of R, then determinant of the product is the product of determinants. But this is a known property of determinants, that they are a multiplicative function. Determinant of the product of matrices is always the product of determinants. So that makes determinant a homomorphism. Oh, but if we have a homomorphism, then we have a normal subgroup. So kernel of the determinant is a normal subgroup. Of GLN of R. In fact, it has a name. It's called SLN of R. And this is nothing else but all the matrices inside GLN which have determinant 1. There are sometimes even descriptive names for these things. This is called the general linear group, and this is called the special linear group. But in any case, so something that you definitely know from linear algebra, determinant, is actually a homomorphism from this non-abelian group. I mean, this group is abelian only when n is 1. So when we're talking about 1 by 1 matrices, so scalars. But as long as n isn't 1, this is a non-abelian group. So determinant gives me a homomorphism from the non-abelian group to the group of units inside the real numbers. And so its kernel is this special linear group. So these examples often arise from knowing about a group from some other perspective. The fact that determinant is a homomorphism is not an easy thing to prove at all, right? That you had to work quite a bit in linear algebra to prove this property of the determinant. Well, one of the prizes you get for that is that you have now produced a homomorphism. So you produced a normal subgroup of the general linear group. So that's what happens, as I said, that's what happens often, that you actually have to do some work to know from some sort of other part of mathematics or other part of algebra some fact, some construction, and if this construction turns out to give rise to a homomorphism, then you now have a homomorphism that's already good. That's already a good thing. And so the homomorphism also gives you a normal subgroup. So in the next lecture, we'll see how normal subgroups can be applied to construct new groups from old ones.